Hello, here we are. We're going to build this model. I'm going to rebuild this model. And this is a Python model using WebVPython, and I want to model and calculate the gravitational field for a hollow Earth. And I wrote about this, and I didn't go over all the details. And do you like my new shirt? If Good People Brewing is watching this, please send me beer. I do like their beer. Okay, so we're going to make this model, but let's just go over some of the important stuff first. Number one, how do we calculate the gravitational field? So if I have a single mass at some position R1, and I want to find the gravitational field at a position RO for observation point, then I need to first find this vector R, the vector from the mass to the observation point. So that's pretty simple, right? It's just a difference. So the going from here to there, I can say the position of this, the position of the observation minus the position of that is that vector R. And then I can calculate the gravitational field due to that tiny little mass. It's just negative g, that mass divided by that magnitude of that distance squared. And then you have to multiply it by this unit vector r hat. Don't forget that. Okay. Now, if I have more than one mass, then I need to just add up all the sums of the vector fields, right? So the gravitational field obeys the superposition principle. Are you ready? I'm ready. Let's get to it. So I've already started. I wrote down the things that I would forget: the mass of the Earth, the radius of the Earth, even though I do kind of memorize those. This is the density of rocks. That's approximately, right? And I'm going to use that a little bit later. So let's just start. Let's just make our Earth, which is really easy. Earth equals sphere, position equals vector 0, 0, 0. And then the radius is equal to RE. Now, here's the cool part. Texture equals textures dot earth run. Is this big enough? I hope this is big enough. There you go. There's your model of the Earth, 3D model. Pretty nice. You can zoom in, zoom out, right? And you don't need that to calculate that, but it just looks cool. And now I want to place uniform masses, break this into a bunch of tiny masses, and calculate the gravitational field due to each of these masses. That's what we're going to do. It's going to be great. So n equals, let's just do 100. I always like to start small, right? N equals 0. So I want to make 100 masses. I'm going to spread them uniformly throughout that Earth. That's what we're going to do. And then, so now I do need a couple things. One, dm is going to be the mass of the Earth divided by n. That's the mass of each of these pieces. I need the radius of each piece. Let's call that dr. I'm not sure why I'm calling it dr. Let's call it rm. And I want to see them, right? So they're not going to be actually the correct size. So let's just do RE divided by 50. Let's just see what that looks like. Okay, so here we're going to make this a little bit bigger. Let's make 100 masses inside of the Earth. While n is less than n, do the following, right? Number one, I want to create a random vector that's in a box from negative RE to RE in the 3 dimensions. So I'm going to call this RT for temporary vector, and it's going to be RE, the radius of the Earth. Now I need to generate a random vector, so vector, and in WebVPython we only have one random function. It's called random, and it returns a number between 0 and 1. So if I want between negative 1 and 1, I can say 2 times random minus 1. So 2 times random minus 1 is going to give me a value between negative 1 and 1, right? Because the biggest this could be would be 2, and then if you subtract 1, you get 1. The smallest would be 0, subtract 1, you get negative 1. And I want that in the x direction, random, and minus 1, and in the y direction. That's my vector. Now, let's go up here. BS equals an empty list. I'm going to make an empty list, and then I'm going to add spheres to that list because I don't want to deal with 100 different objects. So instead, I'm going to have them all in this list, and then I can deal with those lists. And I'm going to do this the wrong way first. So I'm just going to add a sphere. So, and if I multiply this by RE, it's going to be now between negative RE and positive RE in the 3 dimensions. BS equals BS plus a sphere. And you can do a pin, but I don't like that. I like to do it this way. A sphere, the position is going to be that RT vector. The radius is going to be equal to RM. Now I need to increase my value of n. N equals n plus 1. And we're not going to see it. I'll show you why. Oh, we will. There's my... See, it didn't. They're not all inside the Earth because I did a cube. And you can't see the ones inside the Earth because the Earth is opaque. I can change that. Opacity equals 0.3. I've noticed if I make things transparent, it slows stuff down a lot. But there you go. There's my 100 masses around the Earth in a cube. I can make them into a sphere by doing this. If I generate my random vector, and then I'm just going to do it if the magnitude of that random vector, RT, is less than or equal to RE. I'm just going to do less than because it doesn't really matter. And then I'm going to add, only if it's smaller than the radius will I add that, and only if it's smaller will I add 1 to my counter. So now they should all be inside the Earth. Right there. There's 100. You can count them if you want. I'm not going to. Zoom in, zoom out. It does look good though. And you can make this 1,000. If you can do 100, you can do 1,000. Right? Maybe a little bit too big, but that's fine. Let's leave it at 100 for now, and then we'll go back. Now, what I want to do is to calculate the gravitational field on the surface of the Earth. So let's make a function that gives us, we give it the point mass, the location of the mass, the value of the mass, and the observation location. And then it returns the gravitational field due to that piece. And we'll call this DG, DG. We're going to give it the location, RMT. I use T for temporary. The mass, MT, and ROT, the temporary observation location. And so the first thing I want to do is to calculate that vector from the mass to the observation. So these are going to be vectors. Vector, that's a scalar. So this is ROT minus RMT. And I think I'm ready. Return G times MT times norm RR. Right, so norm gives me the unit vector. And then I need to divide by the magnitude of RR squared. So that should do it. Oh, not DF, DG. There we go. Okay, so now let's pick an observation location. Observation is going to be on the x-axis. It's just vector RE00, 0. And what I want to do is go through all of my masses, calculate the gravitational field, and add it to the total so I can sum it up. G total equals 0. Right, I have to start with a value. If I want to calculate a gravitational field and add it to this, I have to start with something. So I have to start with 0. Now I need to go through all my list of balls. I'm calling them balls. This is a list of balls. And I can do that quite easily for B in BS. So this will go through the list. And every item in there, it will call B. And so I can reference that as B. So what I want to do, I want to calculate, I can do this all in one step. G total equals G total plus DG. Now, the position of that's going to be B.POS, right? Because these have a vector location, but it's in the position because they're actually objects too. So I can't just say, that's how I reference that value. The mass, they're all the same. DM, I calculated that up before. And then the vector location is OBS. That's it. Now I just need to print it. Hopefully, what do we want to get? Right? If it's the mass of all of those things, it has the mass of the Earth. If you're looking outside of it and it's spherically distributed, it should be negative 9.8 in the x direction, 0 in the y and z. But it won't be. Print G surface equals G total. and we'll use newtons per kilogram. Let's run it. So I got 22, 10, 5. It's even in the wrong direction. Did I leave off a minus sign? I did. Yeah. Negative. Let's run it again. Okay, that's not bad, right? -7, it should be -9.8, and these should be 0. And that's just with 100 masses. Let's ramp it up to 1,000 masses and see what we get. I'm going to turn off the Earth and then put these at 1,000 and run it. So there's my Earth. You can't see the Earth, but there's my 1,000 masses. And that's a pretty good value. Well, if that's good, more is better. So let's do 5,000. And you can play this game and see how far you can get. That's a nice uniform sphere, don't you think? I think. -9.6, 0.22, 0.04. That's pretty good. And every time you run it, you're going to get something a little bit different because these are randomly located. So that one's not as good. Let's do one more. But this shows something. Oh, look at that. This shows something that a spherical distribution of masses, as long as you're outside of that, the gravitational field looks like that point's all at the center. Okay. But now we need to make a hollow Earth. Let's make a hollow Earth. So I'm going to go back to 1,000. Just so it doesn't get too fast. And I'm going to make my thickness 10% the radius of the shell. The shell's going to be 10%. So let's do that. Our shell is going to be equal to 0.9 times RE, right? So 90%, that's how much space I'm going to have. Does that make sense? So down here, when I make my my points, I'm going to still make the points, but I want to only include them if they're inside the sphere and in the shell, right? So I can go over here and say, and mag RT is greater than or equal to, doesn't really matter, R shell. So it's only going to count it if it's in the right spot. It's going to make all these things. It's going to throw away a bunch of them, right? It's only going to keep them if they meet that criteria. Let's do it. And it looks the same, but it's not, right? Because as I zoom in, you can see that the inside's hollow. See, we're inside the hollow Earth. See that? Now, this has the same mass as the Earth, right? Because I used dm is the mass of the Earth divided by the number. So it still has the same mass. So when I run this calculation, I should get this close to the same value for g. I'm still getting around -9.8, right? It's not, oh, yeah, that's only at 1,000. Run it again. Yeah, so it's fine. That one's, but you know, you got to realize if you're really close to one of those points, you can get something really weird. I'm surprised that this is positive. Oh, that's just because it's pushing up. Okay, that's fine. Okay, so I'm pretty happy. But now, what if the density? What if you like remove the interior part? So the density of all the stuff is just the density of rock. So 3,500 kilograms per cubic meter. That's where I got that from. Let's change that. Let's calculate the total mass. So the first thing we need to do is to calculate the volume. So I need the volume of the Earth. It's going to be 4/3 pi times the radius of the Earth cubed. And you can simplify this some, but you don't need to because it doesn't really matter. Down here of the radius of the shell, let's do it over here. The volume of the crust is going to be the volume of the Earth minus the volume of the interior part that I take away, which would be 4/3 times pi times RS cubed. So now I have my volume of the crust. I can calculate the mass of the crust. M crust is going to be equal to the density, rho S, times V crust. Now I'm going to say dm is m crust divided by n, which I have it up there, but I'm just changing it. It's fine. So we should have a lower gravitational field now because the mass of the Earth is much smaller. And there you go. So it's quite small. Now, what if you're in the interior of the Earth, right? If you're in the interior of the Earth, not in the crust, then the gravitational field should be zero, right? Because this is the Gauss's law for gravity. If I draw a spherical shell around the whole thing and there's no mass inside of there and it's uniformly distributed, then the gravitational field should be zero. So let's do that. And so that only counts because the stuff outside is uniform, right? Obviously, if I take the flux of that whole thing is zero, but if I want to calculate the gravitational field, this has to be uniformly distributed. So it won't perfectly work, but it'll kind of work. So let's just move our observation location to inside the Earth. I'm just going to put it halfway, RE over 2, and now let's run it. Okay, there's our Earth. And that's pretty good. That's pretty close to zero. I mean, it's not perfect. We only have 1,000 pieces, but yeah, the gravitational field inside would be zero. Now, if you want a homework assignment, and you do, you can actually it'd be fun to do the same thing, and I will give you a link to the code, and make a plot of G as a function of R, right? So as you get out, do it for a full Earth of uniform density, which is not, and then plot G as a function of R, and then do it for the hollow Earth. That'd be kind of cool, and you can see outside it plots away. I'm not going to do that because I want to show you something else. You could also build a better model for the Earth using there's density functions that you could use, and then you could change it up. So that's your homework assignment for you. I do want to show you one other thing. Let's see if I can bring this up right here. Okay, here we go. So how do we know if the gravitational field doesn't change depending on the inside of the Earth? How do we know the interior of the Earth is solid, not hollow? One of the early experiments that showed this is really cool. Okay, the idea was to try to measure the density of the Earth. So if you take a plum mass and you let it hang, then gravity pulls it down, the gravitational interaction with the Earth. But if you get near some large massive object like a mountain, then there will be an interaction between the mass and the mountain too. And if you could measure, if you knew the mass of the mountain and how far away it was, not easy to do, and you knew the gravitational force pulling down, which we know the gravitational force, right? Then by looking at how much deflection this is, you could actually calculate the ratio of these two forces, and therefore the ratio of the mass of the mountain to the mass of the Earth. We know the size of the Earth. Aristophanes did that a long time ago. It's a really difficult experiment, right? Because there's a really small angle, and how do we measure angle deflections from the vertical? We usually use a plumb bob. So this plumb bob can't measure the angle from itself. So instead, you use a star. And then you also want to measure the angular deflection on both sides so you can see, make sure that you're doing it right. But then you have to take into account the curvature of the Earth. It's not easy. You need the radius of the Earth to find the curvature of the Earth. You need the radius of the Earth to find the value of the distance, this gravitational force. You need to find the mass of the mountain, which, how do you find the mass of a mountain? Well, you measure the properties of it, you assume it's rock, and you assume the density. And from all that, you can estimate the mass of the mountain and the density of the mountain. And from that, you can calculate, by measuring this deflection, you can calculate the density of the Earth. And it's like, 4,500 or 5,000 kilograms per cubic meter. And if the stuff on the surface is 3,000, right, rocks, then there's no way it could be hollow unless we have a crust and it has a way, way, way more massive, way, way higher density, which just doesn't seem plausible. Of course, later you can do things like detect seismic waves through the interior of the Earth, and you can use that to measure the density and all that. But this is a really cool experiment in 1774, and they found this mountain in Scotland that they used to measure this deflection. It's kind of cool, but there you go. Okay, so that's calculating the gravitational field due to a bunch of masses in Python. Code down below. I wrote about this in my Medium blog. If you want to read that, I'll put a link to that down below. There's a good Wikipedia page on this experiment. I'll put a link to that to that down below also, and that's that. Peace out.